Hello, in this section, I will determine where a function is increasing or decreasing using first derivative. So yeah, this is increasing, decreasing using first derivative. So let's say you had a function f of x equals x cubed minus 3/2 x squared. So based on your algebra course, this is a polynomial. It's an odd behavior and it would look something like this. So with calculus, you can actually figure out where it's actually increasing. So when I go uphill, I know I'm increasing. And when I'm going downhill, I'm going decreasing. And then when I'm going uphill again, I'm increasing. So it's increasing here, here, and here. So with calculus, specifically first derivative, we could figure out where those intervals are. So how do you find the intervals where the function is increasing or decreasing? So first, I would find the critical points by taking first derivative and setting it to 0 and solving for x. Okay, so just like the last lecture, we were learning finding local min and local max. So it's like the same step. Second step is using a number line apply test point method. So it's very similar to the test point method. You got to figure out in test point method, you figure out where is positive, where is negative using testing point, right? And then step 3, for a positive sign, that would be increasing. For negative sign, that would be decreasing. And for this one, you don't have to put when you put your final answer, you don't have to put the union. That's where a lot of people make mistakes. You don't have to put the union, but you just have to put like either a comma. And yeah. So for the following examples, find the intervals where the function is increasing or decreasing. So in example 1, we have f of x equals x cubed minus 6x squared plus 15. So I'm not going to really explain what it how to get the graph, because you could just put in Desmo or use your algebra skills from college algebra and figure out the x-intercept and all that stuff. So I'm just going to draw it out. Okay, so it would look like this. It has a y-intercept of 5, 1, 2, 3, 4, 5. It has an x-intercept of 1.97. And then it also has another x-intercept at 5.5. And then another x-intercept at negative 1.4. So it would look something like this. If you want a better image, you could just put this in Desmo. So this is what it would roughly look like. It's a polynomial, it's an odd degree, right? Rises to the right, decreases to the left. So in this interval, this would be increasing, because I remember if you go uphill, you would be increasing. And then when you're going downhill, this would be decreasing. And then when you go uphill again, you are increasing. Okay. So now let's just find it. Not based on the graph, but like algebra, calculus wise. So first you got to find the critical point by taking the first derivative. So if our function is f of x equals to x cubed minus 6x squared plus 15, right? Take the first derivative, so it'd be f prime of x. So these are pretty simple because you just take the power rule. So the derivative of x cubed is 3x squared. The derivative of negative 6x squared is negative 12x. And then the derivative of a constant or 15 is 0. Then what you do is set this to 0. And then just solve for x. So over here, we could take out a 3x. So this would be x minus 4. And then when you solve for x, you get x equals 0 and x equals 4. Okay. So then what you would do, these are your critical values. So now we're going to put it on the number line. Here's 0, here's 4. You have just like, okay, so now we're going to apply the test point method. So we have 1, 2, 3. We have 3 different intervals we have to test. So we got to test in boundary less than 0, boundary 2 a number between 0 and 4, and boundary 3 a number greater than 4. Okay, so if our f, so we're going to put it in f prime of x, not f of x. So if f prime of x is 3x squared minus 12x. So let's test boundary 1. So a number less than 0, we can use negative 1. So put it in your f prime. So this would be 3 times negative 1 squared minus 12 minus 1. So this would be 3 plus 12, which is 15. Now, we don't really care about the number. We just care about the sign itself. So 15 is positive, so we're going to put a plus. And then boundary 2, we got to find a number between 0 and 4. So let me test positive 1. So whenever I put f prime of positive 1, I get 3 times 1 squared minus 12 times 1. That would be negative 9. So this number is negative, so you're going to put a minus. And then boundary 3, a number greater than 4, so let's do 5. So this is 3 times 5 squared minus 12 times 5. And then that output is 15. So that's positive, so you're going to put a plus. Okay. So the positive means increasing, the minus means decreasing, and then the positive. Okay. So where is it increasing? So it's in 2 parts, right? It's increasing from negative infinity to 0, right? So it's increasing here, negative infinity to 0. And you do not have to put the union. You just have to put a comma, and then it's also increasing at 4 to infinity, right? So this is increasing. Now let's do decreasing. So it's only decreasing from boundary 2 because it's a minus, right? So it's decreasing from the x value of 0 to 4. Okay, so that's pretty much how you figure it out, how you figure increasing. Now let's do a little bit more. Let's do a rational function. So this one, I'm going to graph it, but I'm not going to go too much in details because you should know how to do this from algebra. But if you don't know how to graph it, you could just put in Desmos. So what I would do is, so this is rational. So we have a vertical asymptote at x squared minus 9, set it to 0. So you have a vertical asymptote at, so when you add 3, right, you get an x, and then take the square root of both sides, you're going to get 3, negative 3. And what would be our horizontal asymptote? our horizontal asymptote would be at y equals 2. So on the highest power on the numerator, it's x squared. And then on the bottom, the highest power is x squared. So this would be just 1. And what would this look like? It would look something like this. Okay, so vertical asymptote at 3. And then another one at -3. And then a horizontal asymptote at y equals 1. Okay, so when you test points, I'm not going to go into too much details how this why you why you should what certain x values you need to test, because you should know this. But on the side, it would look like this. And then on the middle part, it's like concave down like this. And then on the left side, it looks like this. So yeah, so that's what our graph looks like. So let's find where it's increasing, decreasing. So it does, there is a part where it's increasing, decreasing. It looks like it's, I think it's increasing from -infinity to -3. So that kind of is increasing here. And then it's decreasing from 0 to 3 and 3 to infinity. So let's do that. So we got first find our critical value. So if you take, okay, so if our function is f of x equals to x squared over x squared minus 9, what we're going to do is to take the first derivative is take do the quotient rule. So if you forget, I'll show you. So the quotient rule is f prime of g minus g prime of f all over g squared. So if our f is what is our f? Our f is x squared and our g is this whole thing, right? So f is x squared. So f prime would be 2x. And then g would be x squared minus 9. And g prime would be 2x. So apply the quotient rule, f prime g minus g prime f all over g squared. So that would be 2x times x squared minus 9 minus bracket g prime is 2x times f, which is x squared, all over g squared, which is x squared minus 9 squared. So when you clean it up and FOIL it out, this is what you get. 2x cubed And then finally, when you clean up the numerator, it's going to look like this. Now, your critical points are, it's not just going to be, so you set this to 0, right? So 0 equals negative 18x over x squared minus 9 square, right? So your critical point is where, set this to 0. So your one of your critical point is negative 18x. Set it to 0 and then solve for x. You get x value of 0. And then the other one is where it makes it undefined. So we are a rational function. So it's going to be x squared minus 9 squared. Set it to 0 and then solve for x. So you take the square root. You get x squared minus 9. Square root of 0 is 0. And then solve for x. Take the square root. I get positive 3 and negative 3. Okay, so your two critical values are 0, negative 3, and positive 3. Now let's put it on a number line. Negative 3, 0, 3. 1, 2, 3, 4 boundaries we have to test. So what was our f prime of x? F prime of x is negative 18x over x squared minus 9 squared. So let's test boundary 1. So we need a number less than negative 3. So maybe we could do negative 4. So put it in f prime. So this would be negative 18 times negative 4. So when you do the algebra, you get positive on the top, you get positive 72, on the bottom you get positive 49. So a positive divided by a positive is positive. So that's why you're going to put a positive. Okay, let's test boundary 2. So we need a number between negative 3 and 0. So let's test negative 1. So this would be 18 over 64. So that also would be positive. Positive there. And then boundary 3, a number between 0 and 3. So we can do test positive 1. So that would be negative 18 times 1. So that would be negative 18 over 64, which would be a negative where a positive is negative. And then boundary 4, a number greater than 3. So let's do positive 4. That would be negative 72 over positive 49. So that would also be negative. Okay, so now where is our interval increasing and decreasing? So it's increasing in here, and then it's decreasing from boundaries 3 and 4. So your final answer would be increasing. So from negative infinity to negative 3, and then you don't put the union, just put a comma, and then from negative 3 to 0. And then it's decreasing from 0, 3 to 3 to 4. So that would be from 0 to 3, 3 to infinity. And that's it. That is increasing, decreasing. So the next one would be concavity and where you have an inflection point. So that should be the next video. Okay, that's it. Thank you. Have a great day. Bye-bye.